The first stone hurled by the prehistoric man was probably the earliest example of external ballistics. The advantages of being able to throw further and with more power led to devices such as slings and spears. Next came the bow and an extension of it called the ballista, from which ballistics derives its name. In turn, the word ballista derives its origin to a Greek word, ballin, meaning to throw. There is a wide variety of firearms to be found today. In practice, the various types from handguns through to heavy RT show distinct differences, but from the ballistic standpoint, they are all similar. Therefore, to understand the ballistics of projectiles, it is essential to know its behavior when inside the weapon, outside the weapon, and finally when it strikes the target. The aim of this CBT package is to get acquainted with the ballistics of small arms ammunition. This CBT package will be covered in 5 parts. Part 1, definitions and types of ballistics. Part 2, internal ballistics. Part 3, intermediate ballistics. Part 4, external ballistics. Part 5, wound ballistics. Part 1, definitions and types of ballistics. Definitions of various types of ballistics will be covered in this part. Internal ballistics. Study of events which take place from the moment of ignition of the propellant to the time when the projectile leaves the muzzle and or the rocket reaches all burned position during flight. Intermediate ballistics. Study of transition from internal ballistics to external ballistics, which occurs in the vicinity of the gun barrel. External ballistics. Study of motion of projectile on leaving the gun and influence of emergent gases during the free flight of the projectile in air or water. Wound ballistics. Study of motion of the projectile within the body and their wounding capacity. Terminal ballistics. Study of effect of a projectile on the target. The history of the internal ballistics began with the use of gunpowder dating back to 1320 AD. The study of internal ballistics can be further subdivided into the study of ammunition, the firing sequence, the distribution of energy, and the factors affecting internal ballistics. In a modern firearm, the propellant and the ignition device are assembled as a unit in a combustible bag. The projectile, the propellant charge, the primer, and the cartridge case are collectively known as ammunition. The projectile. It is also referred to as a shot. There are 3 common types of projectiles: the bore caliber projectiles, sabot projectiles, shot. Bore caliber projectiles. They are of the same diameter as the bore, and so their sides bear directly against the sides of the bore. High gas pressure is used for setup, or driving band is used for location, obturation, and spin of the projectiles within the barrel. Saboted projectile. Shot. The term shot can be applied to loosely supported lead shots or lead spheres, or a number of flechettes positioned ahead of the gas sealing wad. Propellant compositions. Black powder, often known as gunpowder, is the modern formulation of the earliest propellant. It consists of a mixture of saltpeter, charcoal, and sulfur in proportions of 75 is to 15 is to 10.
There are three main types of propellants: single-based propellants, double-based propellants, triple-based propellants. Double-based propellants are more powerful than single-based, but cause excessive barrel erosion and muzzle flash. Triple-based propellants are the best, as they reduce these effects by addition of cool burning nitroguanidine. Types of propellant granules. Commonly used types of propellant granules are disc, cylindrical, multi-tube, cord, ribbon, and slotted tube.
Purebird's law. It is assumed that on firing, the entire surface of each propellant granule is ignited almost simultaneously, and all the surfaces then recede at an identical rate. The granules are said to burn in parallel layers. For example, if the initial granule is cylindrical, it will retain its cylindrical shape throughout the burning process, as the diameter and the length of the cylinder will reduce at the same rate. The primer. A primer initiates the burning of a propellant by releasing hot gases and particles into the charge. The firing is initiated by electrical heating or mechanical crushing of the primer.
Ignition. The firing sequence is initiated by the ignition of the primer, which in turn ignites the propellant. The pressure and temperature inside the chamber increase dramatically. The burning rate of the propellant is roughly proportional to the pressure. Obturation. It is the radial expansion of cartridge case inside the chamber. It is caused by the high pressure generated on firing. It seals the gap between the cartridge case and the chamber walls and prevents any leaking of pressure from side and back. Short start pressure. The rising pressure inside the chamber is moderated by the motion of projectile along the barrel. The pressure at which this motion begins is called short start pressure. For 7.62 ammunition, its value is 5 tons per square inch. Setup. On moving forward, the bullet encounters the rifling in the barrel. The engaging of the bullet within the lands and grooves of rifling is known as setup. This also acts as a seal, preventing the escape of gases ahead of the projectile. Peak pressure. This is the maximum pressure generated by the gases in the bore. It is attained when the projectile has travelled roughly 1/10 of the barrel length. After this, the rate of increase of space in the barrel is greater than the gas generation and the pressure falls. The approximate value of peak pressure is 22 tons per square inch and is attained in 0.5 milliseconds. The peak pressure depends upon the rapid liberation of gases and high projectile mass. The rapid liberation of gases is further dependent on the total surface area of propellant granules, the high value of force constant, and the fast burning rate. All burnt point. This is the instant at which the complete propellant has burnt. It is dependent upon peak pressure. If all burnt point is achieved early, the propulsive efficiency increases. Muzzle flash and blast are reduced, and there is an increased consistency in the muzzle velocity. In case the all burnt point is not achieved, a large quantity of propellant remains unburnt. The propulsive efficiency is reduced and an intense muzzle flash is produced. The various actions taking place on the initiation of a round are being shown graphically in the form of time and space curves. Distribution of energy. When a propellant burns, it releases a large amount of energy in the form of hot propellant gases. As the firing sequence progresses, a large portion of this energy is converted into other forms. The approximate distribution of energy in the end of firing sequence is: motion of projectile 32%, motion of propellant gases 3%, frictional losses 3%, heat loss to gun and projectile 20%, heat retained by propellant gases 42%. Certain minor effects include rotational energy to projectile 0.15%, recoil energy 0.1%. Factors affecting internal ballistics. Propellant energy. The propellant energy is in turn dependent upon charge weight, quality or type of propellant, the charge temperature, and the space in which charge is enclosed. Length and diameter of barrel. More the length of the barrel, better propulsive efficiency. More diameter, more volume available for expansion of gases. Projectile. Projectile in turn depends upon mass, which affects peak pressure and surface friction. The material also affects the friction. Shape of the projectile. The shape of the projectile may affect the setup. The cartridge case. The material used in making the cartridge case affects effectiveness of obturation.
Roughly 75% of the available energy passes through the muzzle after firing. Majority of it is carried by propellant gases in the form of heat, pressure and motion. After muzzle exit, the behavior of these gases has considerable influence on the projectile and the gun motions. They also give rise to the effects known as blast and flash.
The release of high pressure gases from the muzzle radiate at the speed of sound as noise and cause turbulence. Noise is generated both away and towards the muzzle. The outgoing waves, on account of sudden expansion, travel at more than the speed of sound, resulting in the sonic bang, and is called the blast shock wave. The incoming shock wave operates towards the muzzle and against the gas flow and forms a quasi-static shock wave called bottle shock. The curved sides of this wave is known as barrel shock, and the flat base is called the Mach disc. The size of the bottle shock varies as per outflowing gas velocity, and with fall of pressure, the shock disappears into the barrel. The incoming shock wave operates towards the muzzle and against the gas flow and forms a quasi-static shock wave called bottle. The release of high pressure gases from the muzzle radiate at the speed of sound as noise and cause turbulence. Noise is generated both away and towards the muzzle. The outgoing waves, on account of sudden expansion, travel at more than the speed of sound, resulting in the sonic bang, and is called the blast shock wave. The incoming shock wave operates towards the muzzle and against the gas flow and forms a quasi-static shock wave called bottle shock. The curved sides of this wave is known as barrel shock, and the flat base is called the Mach disc. The size of the bottle shock varies as per outflowing gas velocity, and with fall of pressure, the shock disappears into the barrel. The muzzle gas flow field during firing consists of two phases. As the projectile accelerates along the bore, it pushes ahead of it a column of air augmented by any leakage of propellant gases past the projectile. A shock wave forms just ahead of the projectile, travels along the bore, and is released as a near spherical precursor blast shock at the muzzle. Once the outflowing air velocity is sufficient, a small bottle shock will form about the muzzle, growing in size as the flow velocity increases. Main blast field. This is caused on account of ejection of high pressure propellant gases. The release of propellant gases from the barrel and their sudden expansion results in increase in velocity and creation of shock waves around the base of the projectile. This gives additional acceleration to the projectile for several caliber lengths. A new barrel shock and Mach disc, ultimately shrinking into the barrel, are also formed. Blast suppression. The blast shock from small caliber guns can be suppressed by silencer attached to the muzzle. A silencer never totally silences a weapon. It just reduces the intensity of the muzzle blast. Consequently, silencers are often known as moderators. The three methods of blast suppression commonly employed in silencers are blast absorption, blast dissipation, blast containment and controlled release.
Flash is the light emitted in the vicinity of the muzzle by the hot propellant gases and the chemical reactions that follow as the propellant gases mix with the surrounding air. Flash occurs in 5 phases. Pre-flash precedes the exit of the bullet from the muzzle, may occur owing to hot gases and particles that have leaked past the projectile. Following the muzzle exit, the temperature of the propellant gases is generally sufficiently high to emit visible radiation, primary flash. As the gases rapidly expand and cool, they continue to emit a relatively faint muzzle glow. They are then recompressed as they pass through the mag disc, and the consequent high temperature produces intermediate flash. Secondary flash, the ignition of hot combustible gases, mainly hydrogen and carbon monoxide, on mixing with atmospheric oxygen produces secondary flash. This is very bright in large caliber weapons but does not take place in small caliber weapons. Finally, hot particles and remnants of burning propellant may appear as a long streak of light in the wake of the projectile. This is called as incandescence. Flash suppression is the process of reducing or suppressing the flash produced on firing of a projectile. The 3 methods of flash suppression are muzzle devices, choice of propellant, and propellant additives. Flash occurs in 5 phases. Flash suppression is the process of reducing or suppressing the flash produced on firing of a projectile. The 3 methods of flash suppression are muzzle devices, choice of propellant, and propellant additives. Muzzle devices, also known as the flash hider. The flash hiders surround the primary flash and hide it from all directions except the line of fire. They also reduce the intermediate flash by dispersing or breaking up the barrel shock and mag disc. Flash suppressor devices commonly used are of 3 types. The conical tube, the slotted tube, the bar tube.
Propellant. In large caliber guns, the most effective method of secondary flash reduction is to use a propellant which evolves a large proportion of inert nitrogen gas at relatively low temperatures. Such a technique will dilute the combustible fraction of the propellant gases and reduce the overall temperature. It is achieved by triple base propellants owing to their large proportion of nitrogen rich nitroguanidine. Propellant additives. Flash can also be reduced by the addition of potassium and sodium salts to the propellant, especially potassium sulfate or nitrate, potassium cryolite and sodium cryolite. They inhibit the formation and burning of hydrogen gas. However, these additives are generally not used because they increase the amount of smoke produced, which provides a strong, unwelcome firing signature in daytime.
Flash occurs in 5 phases. Flash suppression is the process of reducing or suppressing the flash produced on firing of a projectile. The 3 methods of flash suppression are muzzle devices, choice of propellant, and propellant additives.
Propellant additives. Flash can also be reduced by the addition
The study of external ballistics can be divided into the study of factors affecting external ballistics, the methods to reduce resistance, and the methods of stabilization of projectiles. The factors affecting external ballistics can be divided into 3 categories: related to the bullet, related to the medium of travel, and aerodynamic factors.
The factors which are related to the projectile are mass, caliber, the nose shape, the spin rate. The factors related to the medium of traveling are density of the medium, the pressure, the temperature, and the viscosity of the medium. The aerodynamic factors which affect external ballistics are air resistance, yaw, and drift. Air resistance. It is the retarding force acting in the opposite direction of the projectile motion. The air resistance acts in a number of ways. These are head resistance or forebody drag, base drag, skin friction, and excrescence drag.
Loss in energy of the projectile caused by displacing air is called drag. Compression of air immediately in front of the projectile occurs as a pressure wave. Loss in energy due to the formation of pressure waves is called forebody drag. The compression waves bunch up at the nose of the projectile. Hence, more blunt the nose of the projectile, higher the forebody drag.
Base drag. The turbulence formed behind the body of projectile in flight causes a further resistance known as base drag. The cause is a region of low pressure immediately behind the projectile, which results because the airflow cannot return quickly enough to fill the space behind the projectile. The consequence is a vacuum or suction effect which shows itself in the form of resistance to the motion. Skin friction. Additional resistance is caused by air adhering to the surface of the projectile. It is known as skin friction. The air at the surface of the projectile is moving at the speed as the projectile. However, the next layer is moving little slowly and so on outwards. A smooth and polished surface will help to reduce skin friction. Excrescence drag. This arises from protuberances from the shell and can be minimized by eliminating all unnecessary projections on the projectile. Yaw. When a projectile is fired from a gun, its axis does not lie exactly along the trajectory, which is the path of its center of mass. The angle between the axis of the projectile and the tangent to the trajectory is known as the angle of yaw. Two important aerodynamic forces acting upon the projectile which affect and depend upon yaw are drag and crosswind force, and the resultant force is called the overturning moment. Drag. Drag retards the motion of projectile along its trajectory and varies in magnitude with angle of yaw. If the projectile yaws to greater angles by design, failure, deflection or encounter with a dense medium, the drag will increase dramatically. For example, if a supersonic projectile in air yaws to 90 degrees, its drag typically increases 100-fold. Crosswind force. It is similar to the lift force generated by a wing. This force acts perpendicular to the trajectory and in the direction of yaw. It is of zero magnitude at zero yaw and increases with increasing yaw within the limited angles of yaw occurring during normal flight. At extreme angles of yaw, the crosswind force decreases. Overturning moment. The drag and crosswind force appear to act approximately at the same point on the projectile axis. This point is known as center of pressure. With constantly changing velocity and altitude of the projectile, the position of the center of pressure also varies. For all conventional projectiles, the center of pressure does not coincide with the center of mass, so these combined forces produce an overturning moment dependent on the angle of yaw. Drift. A spun projectile will be found to deviate laterally from the original direction imparted to it by the gun. This lateral deviation is called drift. In practice, this lateral deviation is made up of two parts: drift due to equilibrium yaw and drift due to rotation of the earth, which is not applicable in small arms. Boat tailing. Boat tailing is used to reduce base drag. Boat tail is a truncated cone which reduces the pressure drop in the wake of projectile by allowing air to flow around at base. It helps in acquiring longer range than a flat base projectile. Nose shape. The forebody drag is experienced at the tip of the projectile. A smooth nose shape reduces forebody drag. The longer the head of the projectile, the lesser forebody drag is experienced at supersonic velocities. However, the length of the projectile is restricted to 5 times the caliber. Base bleed. It helps in reducing drag for larger projectiles. It involves burning of small quantity of propellant fitted into the rear of a projectile. The propellant burns at low pressure behind the projectile base. The base bleed reduces drag by 50% and the range increases by 10 to 30%. Fin stabilization. This type of stability is called static stability. The fins are fitted to the rear of the projectile to increase the surface area behind the center of mass. If the projectile yaws and begins to move obliquely, then owing to the larger surface area towards the rear, the resultant air pressure acts through the center of pressure near the tail and swings the projectile around its center of mass and on to the trajectory. Fins have a disadvantage of producing large wind effects on the projectile. Spin stabilization. To withstand high pressure in the gun, the base of the projectile must be very strong and therefore thick and heavy. It is also necessary to have a streamlined nose for the projectile to reduce forebody drag. The combination of the two gives the modern projectile its center of mass near the base and its center of pressure near the nose. This results in an unstable projectile. Dynamic stability in a projectile can be obtained by rapid rotation, which produces powerful gyroscopic forces. A projectile which has a large diameter and which is not too long can be made very stable in flight by the spin imparted to it by rifling in the barrel. Wound ballistics. A wound results from the absorption of energy imparted by a projectile when it strikes and penetrates tissue. These effects depend on the size, shape, composition, and above all, the velocity and stability of the bullet. The study of wound ballistics can be divided into the study of the causes of injury, ammunition design and wound effectiveness, the factors affecting lethality, and the study of body armor. Depending on its velocity, a bullet can cause injury in three ways. Laceration and crushing. The main effect of subsonic, that is, low velocity projectiles, is to penetrate the tissues and crush and force them apart. Only those tissues that have been directly hit are damaged, and the actual wound damage is comparable to that of a knife wound. The laceration and crushing effect is not generally serious unless vital organs or major blood vessels are directly injured. Stress waves. When a high velocity, that is, a supersonic bullet, forces a wound track through solid tissue, it compresses the medium in front of it, and this region of compression moves away as a stress wave of spherical form. The velocity of the stress wave is approximately equal to that of the velocity of sound in water, that is 1500 meters per second. Although the inertia of tissue does not allow the stress wave to bring about any transfer of tissue, damage to the nerves may be caused at a considerable distance from the permanent wound track. Temporary cavitation. In case of a high velocity bullet, momentum is transferred to the surrounding tissue, which on passage of the projectile moves and oscillates, creating a cavity temporarily, 30 to 40 times the size of the projectile. This oscillation results in severe damage outside the immediate path of the projectile. The shape of the cavity is ellipsoid. Because of the atmospheric pressure, bacteria, clothing, etc. are sucked in, which cause injury due to infection. Higher the velocity, greater the cavity. Projectile design. For the same amount of total energy expanded, the design of bullet can make profound difference in its effect on tissues. A soft bullet. A soft bullet will flatten on impact, producing much greater surface area and therefore greater retardation. Such a design will produce a very early release of energy. Unstable jacketed bullet. If the bullet is jacketed and is unstable in flight, the energy would be more rapidly released as the bullet begins to yaw. Stable jacketed bullet. In case of a stable jacketed bullet, the energy is dissipated rather late and a longer wound track is observed. The factors affecting lethality are the mass of the bullet, the velocity of the bullet, the rate of transfer of energy, the location of strike, the cross section of strike, the penetration achieved, stability of the projectile, the elasticity or density of the medium, the damage caused, the kinetic energy of the bullet. Body armor. The idea of body armor has been with man since the earliest of times. In modern life, there is a requirement for lightweight armors capable of stopping high velocity shot. The armor used must resist penetration of the projectile and also dissipate most of the kinetic energy of the shot. We shall study the various types of body armor and the effect of body armor on a projectile. Types of body armor. There are three types of body armor: metallic armor, reinforced plastic armor, ceramic armor. Metallic armor acts by totally rejecting the projectile. It breaks up a projectile and distributes the energy over a large area. Metallic armor is best for stopping high velocity projectiles. It can withstand more than one shot in the same area. Reinforced plastic armor protects by partially rejecting the bullet and partially absorbing it. The area hit is partially destroyed and needs to be replaced for future use. The plastic armor is very light in weight and provides protection against low velocity bullets or blast and fragmentation attack from grenades and shells. Ceramic armor makes use of ceramic, which is a low density hard material. It is effective against armored piercing bullets. Effect of body armor. When a combatant not wearing body armor is hit by a projectile, a wound results depending upon the various factors discussed earlier, and the combatant becomes a casualty. However, when the same combatant dons the body armor, the energy of the projectile is not allowed to be passed to the body of the combatant. Depending upon the type of armor used, the projectile is either totally rejected or is broken into fragments and made to ricochet off the layer of the armor, thereby providing protection to the combatant.
The aim of this CBT package is
This CBT package will be covered in 5 parts. Part 1: Definitions and types of ballistics. Part 2, internal ballistics. Part 3, intermediate ballistics. Part 4, external ballistics. Part 5, wound ballistics.